Hello everyone, welcome to today's session. Today we're going to talk about data foundations for generative AI, and in particular we will look into Apache Iceberg on AWS. We will deep dive into the concepts of Apache Iceberg, open table format, and how AWS supports Apache Iceberg in different forms. So let's have a look at the agenda. So as I said, we will talk about open table format, the overview of Apache Iceberg, what are some of the highlight features, how Apache Iceberg handle updates and deletes, and from a table maintenance standpoint or database maintenance standpoint, what we have to do as a user. After that, we will introduce you into SageMaker Lakehouse, concepts of SageMaker Lakehouse, and how Apache Iceberg is integrated into SageMaker Lakehouse. So let's talk about open table format or OTF. OTF typically refers to a data format specification for structured table, especially used in machine learning, data analysis, or any interoperable data system. So this is a term which you will very often hear now, interoperable data system. So with the concepts of generative AI and LLM and data warehousing, everything coexisting together, right? What happens is interoperability between different data systems becomes very critical. So you will see this term used very commonly now, and more systems getting designed using open table format. So data warehouses and data lake. So if you're coming from like typical data analytics, traditional data warehousing systems, you will know the concept of data warehouse and data lake. So it has evolved significantly over time to meet the changing data analytics need. Early data warehouses focused on structured data from transactional system, typically, right, for business intelligence and reporting. They were built on traditional RDBMS system. As data volume grew, new technologies started emerging, right? So the concept of big data came, and we started talking about handling the big data in data warehouse setup, right? Using all this MPP system like massive parallel processing system. Then we started talking about more columnar storage and data compression and such. So this enabled faster queries on large data set. Data warehouse now integrate a wide variety of data, right? It also includes not just structured data, it can also have unstructured data from your social media or IoT devices or any other unstructured data sources. Early data lakes were inexpensive repository where organization could store data in any format, right? So the data governance, metadata, and accessibility were afterthought. So over the past few years, even data lake have evolved to become more structured, and the term data lakehouse was coined to reflect features like schema on read, master data management, and robust metadata. So real-time processing and machine learning capabilities were added to data lake to support operational analytics, not just batch processing. So transactional data lakes or data warehouse architecture were developed to combine the best aspect of data warehouse and data lake. So this enabled transactional analytical workload across batch, interactive, and real-time and requirement. You can see the data lakes are increasingly getting deployed on cloud platform for scalability and elasticity, obviously. So the governance features have been enhanced through cloud capability like access control, encryption, having audit logs. So in summary, both technology have adapted to handle growing data volume, variety and velocity of the data. The lines have blurred between traditional data warehouse and a data lake architecture. So in addition to platform evolution, customer requirement also have changed or evolved over the years. Customer want a single platform for both analytical and transactional, and even with generative AI in the mix. They also want generative AI workloads to be running. So customers are looking for even real-time analytics and insight for compute resources, which can be scaled elastically based on the demand. So the abundance of raw granular data in a data lake enable more sophisticated analytics like machine learning and AI, which would not be possible in a traditional warehouse. So in summary, the need for real-time schema on read analytics at scale for lower cost is driving the adoption of transactional data lake for modern analytics and application. So a transactional data lake, that is the schema on read architecture, allows analysts or data scientists to quickly explore new data set without lengthy modeling. So this drive faster insight. Data lakes have a flexible schema which allows for storing raw unstructured data. The schema is applied at the query time rather than the ingestion time, right? So transactional data lake offer several benefits, including an advanced analytics. It has lower cost because storing multiple raw copies of data for different analytic use cases is inefficient. A transactional data lake provide one source of truth for both batch and real-time processing. Since it's mostly deployed on the cloud, it's easy to scale because you can scale the storage and you can scale the compute as data volume or the type of analytical queries you're running on top of it. And real-time analytics is another need, right? For example, you want to ingest and analyze streaming data into transactional data lake than most of the data warehouse system. And end of the day, everybody is looking for this single integrated platform, transactional. What we want to avoid is siloed data warehouses, data marts, and data lakes. So this consolidate approach enable governance and reduce duplication and improve data quality. In summary, transactional data lake provide a scalable, cost-effective data analytics foundation for the modern data-driven enterprise. To help overcome the challenges of traditional data lake, open table format provide uh, databases like capability while still supporting storage on cost-effective system like Amazon S3, right? So this feature include asset transactions, allowing write to completely succeed or to be rolled back in its entirety. Record level operation, right, allowing a single row to be inserted, updated, deleted. So which was not very easy on the traditional data lake system, right? Um, and the third one is indexes, right? So if you want to improve the performance, in addition to data lake techniques like partitioning, you can have indexes and such. Concurrency control is another important thing, allowing for multiple process to read and write read and write the same data at the same time. And we also need to handle things like schema evolution. You want to time travel, right? Because you want to see like how different versions of data, how the data looked like 2 months back or something like that. So that is also supported. So basically, the three table formats are Apache Iceberg, Apache Hudi, and Delta Lake. So AWS support all the three of this open table format. Apache Iceberg is an open source transactional data lake high performance format for large analytic table. So Iceberg brings the reliability and simplicity of SQL table to big data. Hudi is another open source transactional data lake framework. It also simplifies incremental data processing and data pipeline development. And Delta Lake is an open source framework that enable building a transactional data lake with compute engine including Spark, Flink, Trino, etc. So data lake table format, including Hudi, Iceberg, and Delta Lake, are gaining more and more traction. And due to earlier we were using Apache Hive, so these format have superior capability. They also enable this cost-effective cloud solution for big data analysis, right? So table format technology is essential for big data environment to properly read, write, manage large data set. Let's also have a look at how open table format is getting more and more used in machine learning and AI ecosystem as well. From an ML and a Gen AI standpoint, OTF represents like a standardized way to represent the tabular data, right? For example, CSVs or Excel or anything. So end of the day, you want it in a machine readable format, and at the same time, it cannot be just data. That was like one of the drawback, right? And it has to include metadata, data type, and sometimes even annotations or labels or something like that. So this is the main idea, is it makes easier for models to understand, uh, process and analyze tabular data, right? Example use case: you give a LLM, like a large language model, a table in open table format. It can generate SQL queries, summaries, or visualization based on the structure, because it has data, metadata, it has labels, annotations, and such. And I think we kind of covered some of this open table format benefit. As I said, it gives you the RDBMS capability like asset compliance. It's scalable, right? And there's a scalable metadata handling. We'll talk more about each of these aspect. Another one is like schema and enforcement and evolution. Schema evolution is like, you have a table with 5 columns today and you added a sixth column, right? So that's the schema evolution. Or even you changed the name of the column or data type of the column, everything has to be handled, right? So the past data follows certain schema, and the new data will follow a new different schema. So the query engine has to handle the both. So that is something which OTF, like especially Iceberg, support. And another one is like time travel support. We talked about it briefly. Like if the data, you want to see the snapshot of the data like 2 months back, after all your new inserts and updates, how the data looked like 2 months back. So that kind of snapshotting feature, and you can go back in time and see how the data looked. So that's very important feature of Iceberg. Let's have a look at Apache Iceberg in particular, right? For example, Apache Iceberg, as you can read, it's a high performance format which support huge analytic table. What it does is bring reliability and simplicity, also possible for engines like processing engines like Spark, Flink, Presto, etc. To perform analytical query on top of it. It also supported by ML and GenAI models as well. So compared to Hive table lacked an ACID transaction. There is a um, there were quite a few projects were bringing ACID capability on Hive table, but it kind of with a lot of trade-offs, right? So updating a table would regularly corrupt query results or the table themselves, and especially handling the concurrent writes or failure was not very easy on Hive table, even when the ACID features were enabled. Another one is performance and scale. Listing directories to find data file was too slow process, right? So if you are coming from a Hadoop background, you know exactly what I'm talking about, right? Every time you want to query something, so there was like a backend process. Hive was dependent on many other Hadoop services to do that, right? So the listing directories itself was very slow, and it kind of lacked the metadata, which is needed for example, partition, pruning, or having some sort of push down optimization. This directory metadata kind of lacked that information, so it was very slow and time taking process. Another one was like costly distraction, like for example, schema evolution would corrupt the table, right? So um, and oftentimes when you are changing the column name or something like that, what you need to do is your downstream applications are getting impacted, and probably you need to go and change the code over there. So these are some of the thought while designing Apache Iceberg, right? With correctness, which is like with asset transaction. The changes are only visible after committed. Another one is speed. For example, one query planning and quick dismissal of irrelevant data. And expressive SQL, that is like bringing SQL capability or SQL behavior to data lake. In place table evolution, which is a very critical feature, right? You can have flexible schema and it handles partition evolution and such. We'll deep dive into some of these aspects. And again, there is no vendor lock-in. For example, you are agnostic to any process engine. You can use Spark or Flink or any other processing engine because it's a very it's an open extendable architecture. Again, time travel we touched upon a couple of times. So let's have a look at how AWS support Iceberg. You can see how Apache Spark we support it through EMR, Glue ETL, and Athena. Trina SQL again and data warehousing capabilities, same thing, EMR, Athena, and Redshift. And in Redshift, you can have read Iceberg data direct, except time travel queries, right? You cannot read the old snapshot, but the current data you can read. Apache Flink EMR and MSF is our managed Apache Flink offering. So with additional jar installation, you can read Iceberg dev. Hive again on EMR, and if you're using Python or Ray, you can use Glue ETL. Now let's look at Iceberg table anatomy. So we want to deep dive a little bit behind the scene how it all comes together for Iceberg. So Iceberg typically follow a tree of metadata file that track metadata of table, partition, and data files. Right. So you can see um, on Iceberg anatomy, like on top, there is this Iceberg catalog, right? And what typically catalog does is it points to a metadata pointer, right? A metadata pointer is nothing but it's a combination of metadata file. Uh, so it's a combination of metadata file and manifest list and manifest file. We'll see what each this file represent and what each of these files do. At the bottom of the slide, you can see there is a data file. Ultimately, the data file which is stored in your object storage, right, like Amazon S3. So let's have a look at what each of this section means. So the first one is your catalog. So catalog is the top level component that registers Iceberg table. So it's responsible for storing a pointer. So end of the day, the pointer is nothing but just a URI string, right? For example, S3 data lake Iceberg table. So this is it's just a pointer to the latest table metadata file. So unlike traditional system like Hive Metastore, the catalog does not store a detailed schema, partitioning, or file layout. It only stores a pointer to the metadata file, which is very, very important because it kind of so you exactly know it doesn't, unlike Hive, it doesn't take a lot of time. It's basically reading bunch of pointers at that moment. And why it matters is it enables atomic update to the table definition, for example, schema change or partitioning, and it also make it easy to support versioning and rollback. So the next layer is metadata pointer definition file pointer. So it's a file path, right? It basically point to a file path. It says like S3, my bucket, warehouse, DB table, metadata.json, something like that, right? It's a file path that tells Iceberg where to find the current metadata. So again, it's not showing the data at this moment. It's only showing the current metadata. So the content is basically table schema, partition spec, snapshot list in case of time travel, and file manifest. Since the metadata file pointer is a single value, updates, for example, a new schema, new data snapshot, can be atomically swapped without any race condition or lock. So just to summarize, you have catalog. Catalog is nothing but a pointer to a metadata file. So unlike Hive Metastore, it does not store anything. It's just a URL. and it supports your atomic swap of the metadata file pointer. Now, metadata pointer is again a pointer to S3 path where the latest metadata.json file is stored. So now let's talk about what metadata file is. A metadata file store the table state. Any change creates a new metadata file, replacing the old one with an atomic swap. The table metadata file tracks schema, partitioning properties, and partitioning and other snapshot of the table content. So a snapshot represents the state of a table at some time, and it is used to access table's data file. So you can see there are the concept is it has two, like it has a metadata file which is a JSON format file and contain all the table level metadata like schema, partitioning, snapshot, and properties. And snapshot represents the state of the table at given point in time, and it points to the manifest list. Now let's talk about manifest files and manifest list. So it plays a very crucial role in tracking the physical layout of your data while enable featuring like snapshotting, again partition, pruning, time travel, etc. So here is how they differ and work together. Like manifest file is a data structure that tracks a set of data file, like for example Parquet files. What it contains is file path to data file, partition value for each file, row count, and some other statistics like what is the minimum, what is the maximum, null count. And it also have file level metadata like file size, file format, for example Parquet or ORC, partition values for pruning. Why it is important? Because it enable partition pruning and predicate pushdown, keeps tags for the query optimization, and kind of avoids scanning the entire dataset for simple queries. Now, what is a manifest list? Manifest list is nothing but a file that lists pointers to manifest file. What it contains is a list of manifest file path, snapshot level metadata, and each snapshot has its own manifest list, right? So why is it really important? So it acts as an index to all manifest file for a specific snapshot. Kind of support time travel, like every snapshot has its own manifest list, and it makes an atomic snapshot update efficient. For example, to replace the manifest list pointer in the metadata. Now let's look at some of the Apache Iceberg feature highlight. One of them which we covered is an expressive SQL. So you can pretty much write the same SQL operation like ANSI SQL compatible SQL operation, whatever we used to do in our RDBMS days, right? Another one is schema evolution. Schema evolution gets a first-class citizen treatment in Iceberg. Each Iceberg metadata file pointed to by the catalog contain a version schema. So it has field names, it has field IDs, types, and statuses and things like that. So unlike other system, Iceberg track field using unique field IDs, not just name. This means you can rename column without breaking the readers. So let's have a look at a partition layout here, which is very critical in schema evaluation. A partition layout defines how data is physically organized into partition. Example, it could be by date or region, customer ID, whatever it is, right? So in Iceberg, what happens is partitioning is declarative. What that means is it is defined in the metadata, not embedded in the file path. So that means if you have seen Hive, how it stores is the ultimately the file where the data resides goes into like a folder structure where in the URL of the folder structure, right, you will also see the folder is created based on the partition. So for example, if you have a partition on date or something, in the URL path also you will see date equal to say whatever the date it is, right? So that is not how it works in Iceberg. It's only defined in metadata. The underlying file resides wherever it is. Another one is like it's a schema based. That means kind of track transformations like bucket, for example, customer ID, comma 8, or truncate, product ID 5. So it kind of tracks transformations. Now another one is partition spec, right? So partition spec is, as I said, is stored in metadata. So each snapshot has its own partition spec, meaning you can change how new data is partitioned, and that's very important. You have this table, right? And today the table is partition. As in this example, the partition is based on the month, and here you are replacing that field, and the partition is going to change based on the days instead of the month. And Iceberg will handle it in a high. For Hive, it is not easy to handle, right? Because you need to probably index the data again, store the data again based on the new partitions. Even the older data has to be rearranged. But here it is possible. That means you can change how the new data is partitioned, and the query still query the old data with old layout. So that means multiple partition specifications or multiple partition specs can coexist. Uh, okay, so as in this example, you can see the partition is based on the month, and it got changed partition by the day, and Iceberg will handle it behind the scenes, right? So the whenever there is a data read from the older partition, it use older partition spec, and for the new one it use new partition spec. And even if there is a query which is um, overlapping between old and new partition, it forms like a split plan, and it handles it. So this is one query example, right? So select star from sales where the date is greater than and less than between this condition, which you can see the data kind of cut across different partition specs here. One is based on the date, and one is based on the month, and the other one is based on the day. So you can see when the queries are executed, it forms like two different split plans for the data, and then merge happens while reading the data. Now, another important feature is simplified queries with hidden partitioning. What that means is in traditional Hive style table, you must filter by partition column explicitly in queries. If you don't, partition pruning won't happen. That means lower queries, right? In Iceberg, partition is abstracted away via partition transform, right? For example, like month or bucket or whatever, it's kind of abstracted, kind of hidden from the user. So user can write queries on raw field, and when Iceberg handle the partition pruning automatically using metadata. So that means when you can see fundamentally the difference. You are basically executing the same query. When you execute in a Hive, unless you explicitly mention the partitions in the query, kind of do a full scan. Whereas the same query in Iceberg, you can see the event date, which is the partition column. It's abstracted, it's hidden, but while the query got executed, it smartly and automatically have it. So that means it's a partition. The scan is just a partial scan. Now, another important aspect or important features of Iceberg is tagging and branching. It's a very powerful feature designed to enhance data versioning, compliance, and auditability, and particularly in regulated environments, right, where you need data pipelines, you need to have an immutable and sort of traceability. And in such environment, this is really important feature. Tagging in Iceberg is nothing but it's a named pointer to a specific snapshot. That is a version. Snapshot means a version of the table. Why tag matters is provide an immutable reference to past table states, kind of useful for your compliance, audits, and rollback. And what is branching? Branching in Iceberg is a mutable pointer to a snapshot that can evolve independently of the main table history. Why branching is useful? For example, you are using a sandbox experimentation on production data, right? So production data pipeline or production data the tags are over there, but still you want to create like a branch out of it and use it for your sandbox, and you don't want to affect any schema changes or anything. So you can, if you go and add a new column or change data type, you don't want to break your production pipeline. So that is quite possible in Iceberg. For example, it supports safe schema changes, data test, or you want to do some sort of trial ingestion, you can do that. And eventually, if you want to merge it into main table, assume that you have some experimentation and you want to finally say that, okay, this is good. I like this new column change or data type change. You can also merge, right? So there are multiple use cases. That is main is like a live production table, and another one is a dev branch. You can do a test schema change or data cleanup or whatever you want to do. So this is very from talking from a tagging and branching for the data ops. WAP pattern, which is like a write, audit, publish pattern, is really critical. It's a powerful data workflow model that allows safe, isolated writing of data, followed by validation before making it visible to reader. This is particularly useful in a multi-writer setup. Like for example, if you have a streaming data or something like that, and if you're having like a regulated environment where you don't want to push the change before it is validated. Another one is, especially when you're using S3s and things like that, how we recommend entropy, right? You don't want things to be sitting in, you don't want data skew or anything, so you want to make sure that the folders are nicely split and there is no skew and such. So Iceberg can do that automatically. You see the ultimate data, right? You see that how that hash is created. So Iceberg behind the scenes handle it if it is a hive, which we were doing it while creating the folders and such, right? So with that, let's move on and see how Apache Iceberg handle updates and delete. So there are two important concepts of it here for a common table format concept. One is copy on write. So copy on write is basically, it's a default write model in Iceberg. How it works is when you perform delete or update, Iceberg uh, uh, it rewrite the entire data file that were affected. That means it create a new snapshot metadata pointing to a new file. Old files are left unchanged, and eventually the cleanup process has to happen. So the process is very simple, right? And it's very reliable. It's excellent read performance, maintains strong consistency. But the cons is it's a write heavy operation, right? And it's not optimal for frequent small updates or deletes. So as and when new updates or small updates happens, what it has to do is it has to rewrite the data file and make sure that your pointers are getting changed. So to tackle some of these cons, there is another concept called merge on read. So what happens is in merge on read is it separates data and delete and update logs. For example, it store data file, which is that original immutable file. Along with that, it keep a separate delete file or log file, right? So it's separate file listing rows to ignore. Example, position deletes or equality deletes, right? It kind of stores the delete file. Now, how it works is on read, Iceberg will merge delete file with the data file at the time of query, right? So what happens is, no need to rewrite the large file during small updates. So this is particularly useful, right? You get the gist, like when it is a small update, basically you're creating a new log file or new delete file based on what get updated or what get deleted. So the process is very efficient for updates and delete process, especially the small data. And again, if you're using a CDC kind of pipeline or streaming kind of pipeline, small files is something which you cannot avoid, right? Uh, Again, it's a low latency ingest for incremental changes. Now, cons is, as you would have guessed, it's a slow read operation because during the query time, during the runtime, that is when the merge is happening. So it's more complex read planning. Now let's have a look at update. What happens in update with the copy on write? So as I mentioned, you have your Iceberg catalog, and the catalog typically does it's just nothing but a URL. It points to a metadata pointer, which is a metadata file. So metadata file keep manifest list and manifest file. So manifest list is again list. It's a list which just says these are the manifest file for that particular snapshot, right? And manifest file is ultimately the file where the data files are stored. So while update with copy on write, what happens is your data file your data file is basically getting rewritten, right? So any new operations like updates or anything, a new data file is getting created, and new data file has that entire data set, and you can see how the manifest file now gets pointed, or it has the URL of the new data file instead of the old data file. So you can see uh, uh, how it is pointing over here into the new data file instead of the old one. So with this diagram, you can see earlier the catalog was pointing into metadata file over here. Instead of that, now this is pointing into the metadata file over here, ultimately which points on to the new data file. Again, up with update on merge on read, what is happening is you have your existing old file which is immutable, and you have your log file which has your delete file or log file. So now this is a combination, right? You have your delete file and data file, while the queries are and manifest file is pointing into both. While the queries are being executed, what happens is your uh, Iceberg catalog kind of point to the new metadata file which has the new manifest list, which points to the new manifest file, right, which includes like your delete file and data file. So with that, now let's talk about how the table maintenance are done in Apache Iceberg. So Iceberg maintenance is needed, right? May need for additional maintenance to have like a performant healthy cluster. So Iceberg provide a control plane, right? And it provides procedure which is implemented in Spark, Flink, or Athena. So table maintenance can be managed by user. Another one is table manage user. If you are going through AWS Glue Data Catalog, it provides a serverless experience for Iceberg table. And table maintenance in this case is managed by AWS. So important action when we talk about maintenance is compaction, of course, because you have smaller files, especially in case of merge on read and stuff. You need to combine the delete file with data file. Such operation has to be done, right? So the compaction handles that kind of situations. And expiration is right if you have any retention set and you want to remove the old metadata and things like that, that can be handled. And any unreferenced object, right? You see how different versions are handled, and in case of unreferenced object, you need to make sure that orphan reclamation is done. So again, there are multiple ways to do it, and on AWS, if you're using Glue Data Catalog, then it makes easy to create transactional data lake using Iceberg table, and all the lot of the table maintenance is handled by AWS, right? So it automatically improve performance by storage optimization. With that, let's talk a little bit about SageMaker Lakehouse and how Iceberg get integrated into SageMaker Lakehouse. And you get a lot of the features. Otherwise, which you have to do manually, a lot of the features AWS manages in this case. So we talked about these problems a little bit briefly, like workload-specific stores have created a lot of data silos, and there is no interoperability, and access controls is inconsistent, and you have a very complex architecture because of the data duplication and how the governance happens behind the scene. And end of the day, it is taking longer time to value, right? If you are doing a new analytic use case and such, it takes really long time to uh, from long time to value to support. So in Amazon SageMaker Lakehouse, we are trying to solve some of these problems. Customer may start with a data lake in the traditional sense or a data warehouse, but as time goes by, you will see they also need a lot of purpose-built data store. And the data in the organization grow, and more sources will come into play. So it could be from your operational databases or federated sources. Customer find that they do a lot of work to get this data into data lake or data warehouse, right? So over time, data become redundant in multiple sources, and it's very difficult to manage. So existing lakehouse approach require a lot of trade-offs. There are different flavors of lakehouse, right? Approach that first start as a data lake and extends with DWH capability, which we talked about. Or some customers have data warehouse solution and they start extending it with the data lake capabilities, right? So we hear from customers. Each of this approach comes with a lot of trade-off. Uh, if you are doing, if you are starting with the data lake and your approach is to bring in data warehouse capability, it take away some of the important database capability that are available in database. For example, multi-statement transaction, multi-table transaction, and the interactive queries are very slow, right? And because the system do not come with a built-in intelligent automatic storage optimization. So data warehouse, again, if you're going with the data warehouse centric approach, uh, that are made to work with data lake, what happens is a common pattern is still you might end up creating a lot of data silos. If you have data in data warehouse, it is still logged in. If keep your data in open table format, you don't have an engine interoperability. So let's see how this is handled by some of this customer. We hear from customer it's very hard to have this unified data management. Data come from multiple sources. They need to build and manage pipeline to bring into analytical store, data warehouse, data lake, or sometimes both, or even purpose built data mart, creating multiple copies of data. So that's where we thought of the concept of SageMaker Lakehouse, which brings this unified experience that is like a single source of truth across AWS as well as non-AWS data sources. And you want an open format so that you can use any processing engine. You can move the data from one cloud to another. You can use multiple processing engines, so there is no vendor lock-in associated. On top of it, you need to be worried about the security, right, and the governance and such. So you need to have like a fine-grained access control on top of your data. So with Lakehouse, you get that, right? With a unified view, you have like this data management and technical catalog, and one copy of data sit across your enterprise, and Lakehouse kind of integrates all of it. And now you're getting a unified access. From unified access standpoint, again, we talked about Iceberg, and you are using Iceberg APIs to access all your data. And there is an FGAC, fine-grained access control across all the data, right, to your column cell level. So the use cases are you're making a single copy of data across data lake, or even if you're doing like a real-time analytics, right? You can use zero-ATL integration and such. Even if you're building a multi-warehouse architecture on Amazon Redshift data warehouse, in all these use cases, this concept applies. We talked about Iceberg a lot, like how the architecture of Iceberg and features of Iceberg. So just to summarize, so again, Apache Iceberg file format, it's an open source table format or OTF, right? And it has Iceberg catalog. Catalog is basically managing a collection of table that are grouped in namespace, right? And we see how the Iceberg efficiently work with your metadata files and manifest files and manifest list. Again, table format define how the structure is defined, read or modified in a table. Iceberg design focus on scalability, performance, and flexibility. It also have REST catalogs, right? Allows you to use a single client to talk to any catalog without relying on technology-specific logic. It also delivers scalable metadata management, right? We talked about a growing data set or schema evolution or concurrent access pattern. It delivers the flexibility that is organization can implement custom catalog logic on server side. You can use the REST catalog to meet specific requirement without altering client applications. Here you can see how the customer is solving on Amazon SageMaker Lakehouse, how Apache Iceberg Open API is kind of bridging the gap, right, between your data warehouse and data lake. Um, and another important feature is we talked about the unified aspect of it. So in Lakehouse, you are providing a unified technical catalog, which is a combination of both federated both managed catalog and federated catalog, right? Federated catalogs is anything which you want to federate, like external sources, your additional Amazon S3 table buckets or Amazon Redshift data warehouse. Under the managed catalog, you will see your default S3 catalog and your RMS catalogs, right? So this is one place um, where you don't need to go through multiple catalogs to see the data. You can come through this unified technical catalog. And even if you have any databases or data warehouses sitting on some other third party, for example, Snowflake or something, you can bring the same thing over here. Again, the openness is guaranteed by Apache Iceberg REST APIs. We talked briefly about it, as it follows Open API specification managed by Apache Iceberg open source community. And it's a catalog agnostic implementation. That means you're working with Glue catalog or some other table catalog, it doesn't matter. It provides a catalog agnostic implementation. And you have the REST-based request to a server-side catalog. Again, Apache Iceberg compatibility. Apache Iceberg REST catalog APIs to access all the data, right? You can see a kind of we have Apache Iceberg API layer in between. So if you're talking to your SageMaker through your SageMaker Unified Studio or any other AWS analytical services, or even the third-party application, you get a seamless experience using Apache Iceberg API. Let's also talk about a little bit about the Redshift, right? You have your Amazon Redshift data sitting on in the Lakehouse, and you can access the same Redshift data from Apache Iceberg engines. So that means that it's bringing truly like that unified experience, right? Unifying all your data in one place. So Redshift data is also now interoperable with Apache Iceberg API. Now, again, like you might be using different computation or processing engine for data analytics, right? Impala or Hive or Spark or Glue. This, since it's integrated with Apache Iceberg and support Apache Iceberg API all across, you will be able to use any of this engine very seamlessly through your to your Lakehouse. The important aspect is access control, security, and integrated access control. Kind of supports for the fine-grained access control, right? It happens on the table level, column level, or even cell level. And if you have industry standard access control for third-party engine, for example, TBAC, this is a tag-based access control. So a lot of the times you will not be able to mention it on a column level, right? It's a lot of effort. So if you have tag-based, for example, you are in healthcare or life science and you want to only show certain data based on, say, clinical trial. That's one tag which you are using. So you can tag, you can create that tag and say that these tables, these columns, these cells belong to that particular tag. So it's very easy to manage. And when you add users to that policies, what happens is they will automatically able to see only the data associated with the tag which they are entitled to. And you can also do role-based access, RBAC, which is very common approach, right? So if you are like a data scientist, you want to see certain set of data. If you are like a data engineer, you want to see certain other set of data. So that is based on the roles, and that kind of access pattern is also allowed. And you also do like a zero copy data sharing within and across enterprises. So with that, I want to talk a little bit about the Data Foundation initiative for generative AI, which we are running. It kind of provides like a go-to-market support for partners to assess the data readiness and also to build a robust data infrastructure. So if you want to, if you're interested in partnering with AWS and explore how this initiative can help you, I'm pretty sure that a lot of the partners are doing really great and cool things with generative AI, and especially like the having they kind of recognize having a solid data foundation for generative AI. And if partners are doing some interesting work in that area, or want to learn or want to do some interesting work in that area, should definitely explore this. And there is a QR code over here which will take you to a nomination sheet where you can nominate, self-nominate, right? If you have any prior experience on data foundations. And some of the significance or some of the advantage of this program is that this is how we can help the partner. Multiple channels over here, right? We can help you with the enablement, which includes, guided learning paths and live session with PSAs and solution architects like me. And you also we frequently update, we frequently give enablement sessions on greatest and latest features on Iceberg or Lakehouse or SageMaker as such, right? So you will be all invited to such sessions, and you also get PSA support if you are working on certain solutions or accelerators, or even like a customer opportunity. You get a PSA support for that. Along with that, for go-to-market, you have access to a lot of pre-built sales asset. You get an AWS seller alignment, and you get to access to very exclusive material on marketing campaigns. And there are obviously there are some tools and incentives like Gen AI, SCA funding, and things like that. So you can learn more about it. Again, the QR code is available here. You can self-nominate, or you can reach out to me, and we will have follow-up conversation. So I really hope you enjoyed the session and learned a little bit about SageMaker and Lakehouse and Iceberg concepts. Thank you.